good to see you. Thank you for coming. It's been a really great experience. This is the first time I've done the Chicago GOTO event in quite a while, and we had a workshop yesterday and lots of good sessions today, so I'm very happy to be here and share with you. So the topic of the talk is discovering RESTful web services. So before I do that, I have one thing I must do. I travel a lot. Last year was about 40 weeks on the road. So I actually need evidence of where I've been just to remind me. So if you don't mind, I'd actually just like to take a snapshot. If you just wave and say hello, this will remind me. Very good, thank you very much. So in the future, I can say, oh, that's where it was. Okay. So again, this is me. This is how you find me on LinkedIn and GitHub and Twitter. And I would love to connect with you. I would love to learn about what you're working on in the API and microservice space. What are challenges to you, what are interesting. If you would remind me when you connect, just so mention GOTO Chicago, that would really help me a lot to make sure I sort of place you in the panoply there of people that I keep running into. So I do a lot of training and a lot of traveling and advising. If you're interested in more of the things I talk about, you can visit this site. These slides will be available to you. And there are a few short videos from some other talks I've done, both internally and externally, and that'll give you some ideas about what's going on. So I used to work in a group called API Academy. They were disbanded at the beginning of this year, but it was an amazing group of people. We had about 7-year run, all really talented individuals. I was so honored to be working with them. We traveled around the world and collected information. So this was our book on microservices. You can download a free copy of this book at this URL. Because it was sponsored by CA Technologies, so you can get a free, that's about a 175-page book. You can get a free book out of that. And again, this link will be in the slides when you get them. So I'd be happy to share that. A lot of the things that I'll talk about today came out of our research for that book. This book covers a sort of a general notion of the value proposition and management idea behind services. It's not a hands-on book like the Designing Microservices book, but this will give you a good start. The last book the team released in December was on API management. So I'll just mention this one. I have 2 copies of that book here. I don't have a free ebook copy, but when we're doing questions, we'll have a chance to give away a couple of copies of that book. And you can visit the site to learn more about it. And then finally, this is the book that I'm just finishing up this year. This will be released in the fall with Pragmatic Publishers. It's much more of a hands-on API book. I won't spend any more time on that, but you can follow that link if you want to learn more about it. Please remember to rate the session. This is a chance for me to improve the talk that I do and a chance for GOTO to learn better how to program for the future. So please just take a moment and do that rating. It helps me a lot. I appreciate it. Okay. All of that stuff out of the way, let's talk about what we're here for. So the title is a bit weird. Discovering RESTful Web Microservices. It's a nice little buzzword package, right? I get a lot of things in there. But it really means a lot to me, this notion of discoverability. I think we're getting to the stage in microservices and web APIs and so on and so forth that we need to move beyond writing bespoke everything. I want to use Twilio, I write a client for Twilio. I want to use AT&T's SMS service, I write a client for AT&T's SMS service. We have all these things that we're doing bespoke right now, and that means it doesn't scale. Now, lucky for us, those of us who are paid developers and architects, we get paid every time somebody wants to connect. But in the grand scheme of things, that getting paid every time slows the growth and the creativity of the environment. The web beat that problem and scalability by changing the rules about how you connect it. And I think that's a thing we need to think about. And one of the first parts of that is this idea of discoverability. I did a talk a few years ago on mapping the API landscape. API landscapes are a big part of what we talk about in our management book. It turns out your API is much more valuable when it's connected to another API. And the more APIs we have in the system, the more APIs in the landscape, the more valuable your API can become because it can attach to more and more people. That's called the network effect. They're trying to do this all the time when they're in Silicon Valley. What's a cool product that has a network effect? It's when we add more people, the value of each individual one gets greater. The problem is that doesn't always happen with APIs because APIs are living in their own private world. We need to figure out how to create a map and a landscape where you're adding an API suddenly makes it available immediately to everyone rather than through some extra work. And maps, and I used maps in mapping the landscape as a big part of my discussion because maps are very much what we use today to figure out how to use an API. This is a map, right? It happens to be a map generated through Swagger Hub, right? A lot of us use Swagger. Swagger was designed as this ability to generate documentation and some stub code. We now use it as a way to actually define an API. So this API is defined by some Swagger file which has specific endpoints, URLs and beginnings and endpoints and responses and stuff like that. The challenge is this is a map for just one API. And it's not even a map for just one kind of API. It's not a map for a user management API or a pet store management API. It's a map for this one instance of it, which totally isolates it. We don't have a general map, do we? We have just specific maps. So we've used maps for a long time, right? So when we first started building web sites, we created site maps. We thought maps were really important. We've given up on that idea for the most part, but I kind of liked that period when we were actually mapping out our websites. Think about the way your maps in your phone work when you're driving, right? We want a map of everything to get from A to B. That's how that AI, that intelligence inside that app works. It knows the landscape, it knows the map. Most of us for our websites, we don't know the map anymore, and that's certainly true for APIs. We don't have good maps. What makes a good map? A good map has legends on it. It says if you want to find the city or the castle or the forest or the lake, this is what it looks like on this map. And it's a universal way of talking about things. In fact, we can draw lots and lots of maps and use the same legends or same symbols. And we don't tend to do this in APIs, but we have done this in the web for a long time. Not just this is the about page or this is the who are we page or the FAQ page, but this is the form and this is the link and this is the drop down and this is the selector. We have all sorts of legends that we've built into our webs that we don't have inside APIs. So what I'd like to do is actually stretch this idea of mapping a little bit further. This is a map that an artist by the name of Alex Rivera helped me create. And this is a map of the landscape of creating RESTful microservices that people could discover along the way. One of the beauties of maps is maps don't tell you how to get there, they just tell you where things are. If you'd like to go visit the castle, here's a map to help you get there. And there are lots of possible ways to get there. So what we're going to do is we're going to visit this Omniterra, this world, where there are lots and lots of places. And we're going to use those places as sort of a guide, as a way to kind of remember and remind us what's really going on in the world. And hopefully this will make sense as we get a little bit further. So finally, I have that RESTful web thing. What does that really mean? What am I trying to pull off here? So the idea of the web, or the idea of hyperlinks, is actually more than half a century old. It was first talked about in recent memory by this gentleman, Ted Nelson, in the 1960s, when he coined the phrase hypertext and hyperlink and hypermedia as a way to talk about links and linking between things. It actually exists long before that, all the way to the dawn of the 20th century. We won't get a chance to talk about that. A gentleman by the name of Otley, who's a Belgian, had actually envisioned what the World Wide Web would look like. If you're interested in what sort of a steampunk version, sort of an early tech version of the World Wide Web would look like, look up the word, the individual Otley. I think it's O-T-T-L-E-T. And you'll find an amazing vision of what he called I think he called the world network. But anyway, we've been around for a while. This idea of webs is important. The person who really made it happen for us was Tim Berners-Lee. It took another 25 years, basically, between when Nelson was talking about it to when we actually got a working version of HTTP. And he wanted this idea of a universally linked information system where portability was really important, generality was really important. Portability, generality, that sounds pretty familiar. Now you might recognize this character, Roy Fielding. Roy Fielding is famous, possibly infamous, for the idea of creating a thing called REST, What he did is documented an architectural pattern that emphasizes scalability and component-level interactions and generality. Boy, that sounds an awful lot like the web, doesn't it? And that's because he used the web as his guide when he started to build his notion of what network software architecture could look like. He was trying to imagine what it was right to write software for the network, not software for one machine. The challenge that we'll have, and we'll talk about this some more, is often we're not led to write software for the network. We're led to write software for the machine or the container or the instance. And we don't really think about the network as our composing space. And finally, there's lots of talk about microservices at this event and several others. And you've probably seen Martin Fowler's sort of distillation version of it. A suite of services running in its own process and lightweight mechanisms, so on and so on and so forth. So we have this notion that has gone for the last half century about how it should be simple and light and easy and straightforward to create services. It turns out there are lots of definitions for microservices, but there's some pretty interesting shared features of microservices. You might have heard this one: make each program do one thing well. A microservice is focused on doing just one thing. It's not a monolith of a bunch of things. It's just one thing. Now, whether that one thing is search or user management is up to the individual designer, but it's one thing. And when it's time to do something else, we're going to do that somewhere else. So another big part of microservices is this notion that the output of every service is actually going to be the input of some other service. So we're trying to figure out this idea of composability. We've used things like ESBs and gateways and proxies to do that for quite a while. There are a lot of people that are trying to build services that actually operate just on their own, and they make their own connections. Amazon is actually very good at doing this internally. They create services that talk to each other very easily. Another aspect of this is designing something to be tried early. We say early and often, so there's that minimum viable product idea that I want to build something just to see if it works before I build anything really huge. No big upfronts, no big waterfall experience. That's another big characteristic of these small services. And then finally, we have this idea of actually using tools, writing tools, programming tools to make programming easier, a kind of a weird sort of inception pattern, right? An abstraction of an abstraction. Netflix gave us a fantastic set of examples of how to do this. They write all sorts of things in their chaos army in order to test the code that they've written before they put it in production, right? So they actually spend thousands of hours and hundreds of thousands of dollars to build all these tools to make writing their code easier. Amazon does a similar thing with the way they start individual projects. Etsy does a similar thing with the way they do releases. Etsy releases 30 or 40 times a day. They have a huge infrastructure they built for that. So this notion of actually programming tools to make it better is a real key part of creating small services that work together. Now, I think there are a few people in the room that I recognize that might actually have seen this list before. Has anybody seen something like this list before? You might know it as the principles of Unix. Right? These are actually the principles of Unix from one of the earliest writings about AT&T's Unix philosophy. And this is actually taken straight out of that material. The beauty of that is it's 40 years old. We already learned a great deal from this, right? So we have lots and lots of learning that we can do about how to build services that interact with each other, whose output is input, who are designed to be tried early, all these things. And we do that really well at the machine level. The challenge is doing it at the network level. So I tend to talk about it in much simpler terms: loosely coupled components running in an engineered system. What's a loosely coupled component? It's pretty easy. If you can release your component into the ecosystem, like at your company, without having to get permission from anyone first, without having to make sure somebody else has also changed their service too, then you're loosely coupled. If I have to wait until the data team makes their changes before I can release my middleware, or I have to wait until the front-end team releases their thing before I can release my middleware, that means we're not loosely coupled. It means we're a distributed monolith, right? I think we all experience this. On the web, of course, this is exactly what happens. I can put up a web server anytime, put any content on it. I can link to anybody else, and it works just fine. I don't have to get permission from anyone to do that. Ted Nelson used to say, his idea behind the web should be that anyone can post anything anywhere without getting permission from anyone, right? And finally, running an engineered system, we need an engineered system that's resilient and robust. And we use what's typically called DevOps to do that, right? We have all this process of testing and release, and even testing in production to try to make sure this thing is resilient and it keeps running even if something fails. And that's what the web does. The web keeps running even if my server fails, right? There are no fatal dependencies on the web. It's actually a web, not a stack, right? So it's not like I'm traveling down and if one of these is broken, nobody else works. What's really interesting is the failures on the web are pretty much not on the inside, they're on the outside. They're on the discovery end. If DNS fails, a lot of us are in trouble, right? Now, we've done a pretty good job with Amazon and a few other things of actually creating fatal dependencies. If Amazon's down, a lot of us are down, right? So that's not a web anymore, that's a stack. And we need to fight that in the long term if we're really going to create systems that are robust and live for a long time. So I told you I do a lot of traveling. This is my commuting vehicle. This is how I got here. It only took me an hour. Sometimes people have to drive an hour to work every day. That's what I did. I just flew. But this is also another way to travel, traveling the network. We don't think about it, but we travel the network when we use our browser. We go to lots of places. And that means we need to be programming the network. There are lots of people who are programming different bits and pieces that I all have pull into my web page or pull into my app at some point along the way. And they're all disparate elements that don't really understand a lot about each other. We used to call them iframes and stuff like that, but they're all individual pieces. Often we're tricked into doing this. We're coding one machine. We think the machine is our only target. This happens to be my machine. This tells me I'm not going to be watching a movie on this flight since the system won't reboot. But actually, this is what we program, right? And the problem is when we use our APIs, when I use APIs from Salesforce or SAP or Oracle or Microsoft or Google or whatever, I'm using APIs that I don't control, written by people I've never met, running on machines I can't reach. That's the feature, that's not a bug. Most of us build in our heads systems where they own everything. I own all the servers, I know everybody who's contributing to it, and we all agreed ahead of time how to do it. But that's not how the web works, right? So if we want to scale to the point where we can do our own services anytime, anywhere without permission, we need to get to the point of thinking about the open space rather than the closed space of what programming looks like. Okay, so with that in mind, let's do a little traveling. We're going to go through a couple of places. We won't have a chance in this talk to visit all of the locations on this map, but I want to visit a handful of these and talk a little bit about this and just give us sort of a chance to learn a little bit. And the first place I want to visit is actually in the center. This is what I call the ruins of Monolithia. This is the place where all of us remember, right? This used to be a thriving society. This used to be a fantastic place. It turns out it was originally designed by a king, by a royalty. There's this line of royalty, and this first king designed this community and figured out where all the roads would work and where all the communities are, and everything went great. And it took a long time, but we got it built up. And matter of fact, it took that king's whole life. And by the time the king died, his sister took over, and she took on the task of architecting the rest of the community. And what she decided is that that last architecture that her brother had worked on was really not all that good. So what we're going to do is we're going to build a brand new architecture. We're going to get rid of all that old stuff. And we're going to build a new system instead. So that meant that there were lots of parts that weren't quite working well anymore or didn't connect really well, but people kind of got used to it. And then she died, and then her brother took over. And then he started tearing up the old system and building the new system again until pretty soon, centuries, decades after decades, generations after generations, the entire community was always in flux, was always being built. Nothing was working anymore. It was always either old and abandoned or yet to be built. And we had this community where nothing worked anymore, and it took too long. By the time we built it, it was old and unusable, so somebody had to build something else instead. And it suddenly fell to ruin. Nobody knows quite sure how it all ended, but apparently what happened is people just abandoned all this architecture and went off somewhere else to do something else. Now this probably rings true in a handful of ways that we can think about, right? A lot of us work in organizations where we're constantly rebuilding what was already there. Somebody new comes along, there's a new technology, there's a new way of doing it, we're just going to rebuild what's there. In fact, in real life, what we do is we repurpose what already exists. What used to be a church is now a community center. What used to be a factory is now an apartment building. We actually reuse what's there rather than destroy it. Although in America, we're pretty good at tearing down buildings. Europe's a little better at keeping them. In America, we're pretty good at like just moving that stuff over somewhere else. So it turns out this idea of building a huge community is complex because it's distributed in lots and lots of ways. So you've probably seen this list before, some version of this list. The fallacy of distributed computing. Peter Deutsch is the person who's sort of credited with the first version of this list. I think he had maybe 5 or 6 things on the list. It's grown since then. A lot of these fallacies probably look familiar. That we always assume that the network is totally reliable, right? We always assume that latency is 0, or that the bandwidth is infinite, or that the system is already secured, or that nobody moves the server from one place to another. There's only one administrator. If I could just find her, I could get my problem solved, right? That transport cost from one place to another is 0. It turns out none of these things are true, right? None of these things are true. There's always latency. There's always a bandwidth problem. The network is always going down somewhere on the planet. Somehow we need to account for that when we design and build what we're doing. I love this line from Pat Hellen. Pat Hellen started working at Microsoft, and then he moved to Amazon, and then he helped Amazon build their distributed system, and then he moved back to Microsoft to help them build Azure, and now he's working at Salesforce. And he's got this line in a paper called Data on the Inside and on the Outside. There's no simultaneity at a distance. What does that mean? I look up in the sky, and I look at a star, and I say, oh, that's a beautiful star. What I don't realize is that star is tens of millions of light years away, and that star is already dead. I go to a website, I hit this API, and I say, how many of those cool Mike Amundsen books do you have in stock? And it says 1. And by the time the message gets to me, the book is gone, right? We imagine that everything is instantaneous, but it's really not, right? And that's a really important part of programming the network. Program for the fact that it takes time to go from place to place, and that every information, every message that's sent is really a message in a bottle, and it's frozen in time, and the amount of time it travels affects the accuracy of that message. Yet we commonly don't think about that when we write our own apps. We just imagine that latency is 0. And this is another one I like from Michael Nygard. I'll be quoting some other Michael Nygard stuff in this talk. He has a great book called Release It. Michael says bugs will happen. They cannot be eliminated. They cannot be eliminated. So they have to be survived. John Gall, I won't get a chance to talk about John Gall. He's got a great book called Systemantics from the 1980s. And his line is, a quality system is one that keeps running even when it's in failure mode. Even when parts of it are failing, it keeps going. That's how our bodies work. When I got a cold, when I'm not feeling well, I keep going. Often that's how our cars work. That's how so many things in our life work. But often we don't create programs, we don't create applications that actually behave like that. They're brittle. One thing fails and the whole thing falls down. So Michael has a lot of stuff to teach us out of this book called Release It. Has anybody seen this book before? I highly recommend, if you haven't seen this book, to pick up a copy. This is actually the 2nd edition. He wrote the first one, I think, around 2007 or 8 or 9. This one was just released last year. Highly recommend this book. It is primarily about writing code like TCP/IP related code. So if you're a service provider or you're writing client apps, this may not seem appropriate. But especially if you're involved in network apps, he's got some great advice. He has these things called stability patterns and capability patterns. So I want to talk about his stability patterns in this idea of how we program the web. So you've probably heard some of these before. The timeout pattern, right? What is that? That's when I make a request to you and I'll wait 500 milliseconds and that's it. Then I'm leaving. That's it. I'm not going to listen anymore. You've got a certain amount of time. Then there's the circuit breaker, right? Which is when you don't get back to me, now what do? What I do is I mark your server as unreliable, and I flip a switch, which basically takes me to either the alternate place or a cached version of what I got last time, or a message that says, I'm sorry, I can't help you, right? I flip a circuit breaker. That circuit breaker has a timer on it, like another 2,000 milliseconds or 3,000 milliseconds, and then it flips, and I'll try you again, right? So this is a way of kind of mimicking the electric circuit pattern for services to make sure we don't get stuck along the way. So another one called bulkhead. Bulkhead maybe could save me from a circuit breaker. So a bulkhead is when I have a service like one that generates a date time stamp to the microsecond, and everybody uses that service, so I really want to make sure that if it goes down, I don't get in a lot of trouble. What do? I get 6 or 7 of them running in a cluster, right? So if I can get up to 4, 5, or 6 of them, I'm well into 5 nines of reliability for the most part, especially for stateless servers. If one of those goes down, somebody else can answer the question, right? So I can use a bulkhead to help me add reliability. Steady state, this is actually a really nice one. Steady state is this ability to keep running even when things go wrong. Those of us who know about writing logs to disks know that eventually run out of disk space, right? A steady state implementation makes sure I never run out of disk space. It says it notices, boy, you're going to run out soon. Let me go ahead and start getting rid of some of these old logs, or maybe stop writing logs, or maybe write them to somewhere else. There's all sorts of ways to keep the system up and running. System's running too slow, Kubernetes spins up another version of it, or Amazon will spin up another version of it, or Heroku will spin up another version of it, right? That's a steady state implementation. Fail fast is the opposite of timeout. If you send me a message and you say you've got 200,000 milliseconds to answer, and I know from my past history it takes me 300,000 milliseconds to compute this value, what'll I do? I won't even waste my time. I'll just say no. I'll say 500. I can't do it in 200 milliseconds. Go find somebody else, right? So that way we don't back up a lot of people waiting a needless 200 milliseconds because I wasn't going to get it done anyway, right? So fail fast is a really nice pattern. I think Netflix uses that a lot. And finally, there's this handshaking idea. Handshaking in TCP/IP is all this extra talk. I'm about to send you a package. Are you ready? And somebody says, yes, I'm ready. And says, okay, so I'm going to send you the hash and the length. If you got the hash and the length, yes, I got the hash and the length. Okay, here's the message. Did you get the message? Yes, I did. Did it match the hash and the length? No. Okay, I'll send it to you again. Like we have this constant conversation of handshaking, right? We don't really have that on the web, but what we do have are health checks. Are you up? Are you running? What's your memory situation? What's your latency situation? How many errors are you producing? So that's a way of doing handshaking. If I look at your latency situation and I realize your latency is running at 300 milliseconds, I might not even send you the request for the service in 200, because I need it in 200 milliseconds. So I can avoid trouble if I use handshaking. So we're taking this journey, we're taking this step, these things along the way, to help us figure out what's going on. So now I want to talk a little bit about code. I don't know or normally talk about code, because code happens on a machine. I usually like to talk about the network, but I think it's worthwhile talking about it a little bit. It leads us to a few other places on our map. And the first place I want to talk about on the map is the fields of purity. This is sort of an amazing place in Omniterra. Everybody does one thing and one thing well, and they're amazingly fast at it. So there's all these gurus, all these swamis, all these sorcerers, all these amazing people that do this one thing, and they're amazing. And what you can do is you can sort of just ask them a question, and they answer immediately. What's really weird about it, though, is once they answer your question, they don't remember anything anymore. So you have to ask them again, and you have to ask them again. They have no memory of time. They have no memory over space. They just keep repeating the same thing over and over again. And that's pretty much what a stateless microservice is. A stateless microservices are simple processors like converters or translators. They actually just do one job and do it over and over again. What's amazing about them is they have no dependency on any other service. They don't have to ask anybody any other questions. Return me a list of valid zip codes. Validate the zip code that I have. Tell me what the interest rate is for this currency in this location, and so on and so forth. They're really good at answering just one question and doing it well. They don't even depend on writing or maybe even reading local data storage. All the data may be up in memory, so they can just do it in memory really, really quickly. This turns out to be the most common microservice component example that you'll hear about. We all want stateless services. It turns out it's the least useful. pretty hard for me to get a lot done when all I have is a stateless service or a bunch of stateless services that don't remember anything. I can't write any data. I can't read any stored data. I can't actually execute any series of steps that anybody would actually commit in any kind of way or remember in any kind of way. But they are handy little tiny services. Now what's great about them is they have no shared state. They don't need any other server to explain anything to them. They don't look on another server for data. They don't write any data. They don't wait for somebody's cookie or session or anything to tell them what's going on. They just do their own problem. What's great is they can be easily replaced. I can write my currency translator in PHP today, and I can write it in Go tomorrow, and nobody cares. I can write a bunch of them. I can have them do lots and lots of things. I can actually scale a lot of them. So I can have 10 of them or 12 of them in a cluster or whatever. Or I can spread them around. I can put them at various locations around the planet to make it easier for you to find and connect to them. So often they just look like this. Like this is a little conversion server. It says I get a request and a pointer to responses. I convert the value in the request and I send it back to you. It's simple. It's easy. But there's that thing, right? What about the network? What happens? What happens if it takes too long to work? What happens if I can't connect to the service at all? So when I call this service, what I have to actually do is maybe use this fail-fast idea. Say, look, I have a time budget. I need it in a certain amount of time. Why don't you try it? And if it's not going to work, then I'll just return the value. I'll just say I'm failing, right? So I've got to make up for the notion that it might take too long. I also have to make up for the notion that it might not work. I might not be able to connect to it at all. And we'll talk about that in just a second. So that leads us to another place in the map, and this is the Caves of Persis. This is an amazing place. These are these storage caverns. There are people who work in these caverns, and then they store all the valuable things from the city. People come out to the city, and these are sort of this like priestly class, these sort of ascetics, these religious folks, and they take your object. Maybe it's all of your ceremonial object from the harvest season, and they give you little slips of paper that have IDs on them, and then they go hide them somewhere in the caverns. And the caverns go on forever and ever. There are some people in the caves whose only job is to make new caverns, is to like dig out new parts of the caverns. They never even see the light of day. And they keep storing everything. And every once in a while, they rearrange all the storage inside the caverns. They move things from one place to another. Nobody on the outside actually knows where anything is. They just come and they present their little slips of paper, and somebody says, okay, we'll go get it for you. Sometimes they can get it quickly. Sometimes it takes a while to get it. Maybe it'll take even days to get it. What's really interesting is what happens is over time is they've stored all these objects, and some people never show up with their slip of paper anymore. They don't ask for them anymore. Right? So you might think that what they do inside the caves is they throw away all these things that nobody asks for. But that's not what they do. They keep them forever. They maybe move them to some other place, but they never know when somebody might come back and ask for this, right? So they keep them forever. And it turns out that's exactly what our data storage systems are like, right? There are people whose only job is to figure out how to optimize storage. They don't know anything about the services in front of it. They don't know anything about interfaces or APIs or any of that. All they know is about their storage. And they keep stuff around forever and ever. And to them, it's all just storage. It's all just value in some kind of way. And that leads us to another kind of microservice, and that is this thing we call a persistence service or a storage service. Simple storage that reads and writes, often local data. Like it's on the same server that has the API. It's very disk I/O dependent, so that means I've got disk space, I've got latency, I've got all those reads and writes that I need to deal with. That may also mean that it's really a virtual disk that's spread over against a lot of space that I have to deal with. It may be on the same virtual machine, or it may be dependent on another VM or another 1U in the same rack, but usually it's pretty close together. So these persistent services are often very much needed microservice component, but they're not the easiest to implement because they're stateful, right? So that means they have to memorize things. This is especially important when you have dozens of people that want to access the same storage. Maybe read the same records, maybe update the same records. Suddenly, a distributed system becomes more challenging. They're often treated as a system of record or a source of truth. This is the one database there's only one database, there's only one instance of this one thing somewhere. When in truth, in real life, that's not really true at all, right? We have information all over the place. We have copies of information all the time. We have information on the TV, we have information on the web, we have information in newspapers, we got little slips of papers we were handed when we came in here for registration. There are all sorts of copies of everything, right? We don't necessarily always go back to the record, system of record or the source of truth. We use the copy we have. So it's relatively easy to scale reads for persistent services, mostly through a pattern called CQRS, Command Query Responsibility Separation. We'll separate the reads from the writes. So it's actually pretty easy to scale reads. We can actually make lots of copies of the data and people can read them. But it's a real challenge to write because I don't have things like two-phase commit or cross-service or cross-table commits in any way. Instead, the most typical pattern is to use a thing called a saga pattern. Has anybody heard of a saga pattern? Chris Richardson, who's speaking here and doing a 2-day class at the end of the week, has a great write-up on how to use 2 flavors of the saga pattern to get things done. Amazon uses the saga pattern every day. You go order something from Amazon. You say, I want 1 copy of this book, and I'm going to pay with this credit card, and I want you to ship it like this. And Amazon says, you're all set to go. Of course, they're lying. They haven't tried it. They haven't looked at any of that yet. They just say, yes, go ahead, move on, move on. And then they go back later, and they check, and my credit card is bad. So they're like, hey, you know that credit card? You might want to check that. And then I'll say, oh, all right, never mind, cancel the order, right? So then they have to undo the shipping part, undo the charge part. Well, it's never worked anyway, and put the thing back in stock, right? Those are the sagas. Those are the compensating transactions. And that's how banks work as well, by the way. Banks don't change money in real time. They change money once a day. There's a commit at midnight in the ACH system in the US. Everything else is all just transactions that will resolve later sometime. So it turns out persistence often is I want to write something to logical storage, and there are a lot of possibilities that could go wrong. So what if it takes too long? What if the dependent service on the other end doesn't respond in time? What if that service is down at the other end? Or what if the network is down at the other end? What if data overflows? In other words, it actually fails when I attempt it? These are all things we have to deal with. So now I have a bunch of things from Nygard that I need to employ. I have to make sure there's a fail-fast so that I can tell people to go away if I need to. That's sometimes referred to as a back pressure. I'm probably going to use a timeout when I call the other service, when I try to write the data to that remote data service. I may need a circuit breaker. If I can't write it here, I'm going to have to write it maybe to a queue to be handled later. I need steady state. I need to make sure that the disk doesn't run out, that I don't run into trouble somewhere along the way. So there's a lot of stuff to do. So I want to talk about one more thing, and that's the aggregator service. This is the marketplace of Aggregato. These are all the scholars. These are brilliant people. They're kind of like our sort of stateful people in the fields of purity, but they actually can put things together. You ask them a question, and they know all of the people that they can talk to find the answer to the problem. And they arrange all of those people together. It may take a little bit of time, but they figure out how to solve your problem, even though they don't know a thing themselves. All they know are other people who are smart. And they arrange it all together. And they're an amazing, amazing group of people. And you can go to this marketplace and you can ask people questions. And if they know the answer, they'll arrange to get all the people together to solve your problem quickly and easily. And that's what aggregator services are like. Aggregator services depend on other distant microservices. They might be next door, they might be around the world, they might have moved from yesterday to today. So you're very network dependent. If the network is down, I can't get my work done. There's a lot of challenges there. They can sometimes also be disk I/O dependent. Either there's a local dependency to keep track of state, or there's a dependency somewhere else along the line. This is actually the most often needed service, the aggregator service. This is where we think we're actually going to get our work done. We're going to use lots of microservices to solve our problem. It's actually the hardest to do. It's incredibly hard to do for lots and lots of reasons. The biggest reason is the relativity of time and distance. When we're crossing distance, when it takes time, lots of things can go wrong. So one way to work on time is this difference between sequence and parallel calls. How much can I parallelize when I'm trying to orchestrate a lot of services? How much do I have to do in sequence? And this actually can affect the way you design a service as well. If I need to create a new customer, and then I need to create set of accounts for that customer, I got to wait until that customer record comes back so I have a customer ID to create the accounts. However, if I can create a customer and the accounts at the same time and then associate them in another step, I can parallelize that action. Right? So there are lots of ways that you can design systems to improve your ability to deal with time. Sequence is important, but it's not always important. They should be easy to scale, but because of what I just described, it could be really challenging. Most of us think of getting work done in a sequence. Step 1, step 2, step 3. We sort of live in this Newtonian world where we think that everything happens as an action and equal reaction. We forget that actually we were told more than 100 years ago that we live in a relativistic world where time and space are relative, where they don't happen in a sequence and an order. There's actually a lot of randomness in the world, and we could design systems to take advantage of that. So I've got a lot of databases. I need to gather all those resources and return them based on some query request. Do I have to do them in order, or can I do them in parallel? There's lots of things that can happen here. It could take too long. The dependent service doesn't answer. It might be down. There might be an overflow. Maybe it's unhealthy. It's working, but I can't write data properly. What happens if the traffic spikes suddenly right in the middle of something? There's lots of things that go on. So I need to employ lots of these things we talked about earlier. I need to manage handshaking to check people's health, and I need to probably start to come up with some bulkheads to save me from a lot of trouble. So it turns out there's a lot going on there. It turns out most of your microservice code, especially your aggregator code, is dealing with the network and not dealing with the service at all. There's a great line inside Nygard's book. Is all this extra code, this clutter necessary? It turns out the answer is yes. The short version of this is nobody calls you up if you're working in a company in IT and says, by the way, I just ran a transaction and it worked great. Thank you very much. Hang up. No, they don't do that, right? They only call you up when it doesn't work great, right? Hey, this thing isn't working. I can't find it, blah, blah, blah. So all this clutter, all this dealing with all of the randomness of networks is to prevent those calls from happening. Now, we're not going to have time to go through this next section because I want to leave some time. Do we have some questions? Not yet. Okay, so maybe I'll talk a little bit more. Please be sure to add some questions in there, otherwise I won't be able to give away books. So I'll talk a little bit about some things after this. We're not going to get a chance to talk about all these details, but you'll get the slides afterwards. I want to go back out and talk about another interesting place in all this, and this is the Gardens of Semanya. This is the place where everything kind of gets put together. There's an amazing group of people in this community that actually know how to sort of create messages through flowers, flower arrangements. They actually speak to each other by arranging these different colors and shapes and flowers. What they're really doing is they're actually integrating a lot of things together. They're actually using a unique language that's usable by all these different communities who speak other languages. It's a generalized universal language. That's what Interop is. In the web, our interop happens through a language of HTML. Right? It's the language of the internet. It's the language of the web. So I can build an accounting system with that language. I can build a content management system with that language. I can build all sorts of things with that same language over and over again. I don't need to know about your objects. I don't need to know about your data model. I don't need to know about anything. Interoperation is peer-to-peer. And it works because we have a shared semantic understanding. What happens is the clients and servers on the web understand HTML and HTTP. They understand the message protocol, and they understand the content of the message, which is HTML. CSS and JavaScript is actually just an add-on, by the way. It turns out we're now so dependent on JavaScript, it's no longer an add-on. Our apps don't work anymore. And that is not a language that's shared. The JavaScript language is shared, but what it's talking about is not shared. I'm going to talk briefly about this idea of sign, signal, and symbol from Jens Rasmussen. This idea that we can break up the way we think about things. We get some signal, like it's hot in here, and that's a sign of something, which means maybe it's getting past some comfortable point in the temperature, and that usually symbolizes that somebody needs to go adjust the thermostat somewhere. When we start to create autonomic systems, we have to deal with signal, sign, and symbol. Our brains deal with it instantly. We don't really think about it in broken spaces. Signal is the protocol, and that protocol is usually things like HTTP or COAP or MQTT. Signs are the formats like HTML or HAL or collection JSON or Siren or Uber or Mason. By the way, not XML or JSON. Those are not formats. Those are just serializations like plain text, right? Symbols, symbol actually represents what something means. There are vocabulary managers like Dublin Core Application Profile or Application Level Profile Semantics. These are languages, these are formats that help us share a language together. All right, do we have some questions yet? Oh, we have some questions. Okay, great.